Welcome to Engineers Mindset. Now, let's talk about polytropic processes. Polytropic processes are simply processes that relate pressure and volume as a system changes from one equilibrium state to another. It is given mathematically as PV to the power of n equal to a constant. Okay, so let's simply say PV to the power of n is equal to K, where K stands for what? Constant. Okay, so that's a mathematical relationship for a polytropic process, where n is called a polytropic index of expansion and compression. Okay, now the polytropic index of expansion and compression has a value that ranges from 0 to infinity. It has a value that ranges from 0 to infinity, but three special values of the polytropic index are of utmost importance, and those values are simply 0, 1, and infinity. So let's study when n, okay, when n is equal to 0, 1, and infinity. So these are the three special values of the polytropic index of expansion or compression. So we're going to study these values and see what we're going to obtain in the polytropic process. Now let's consider when n is equal to 0. So consider when n is equal to 0. If we do this from the law or from the formula of the polytropic index, we have PV to the power of 0 is equal to constant. So if n is 0, it now implies that if n is equal to 0, so it now implies that P v to the power of 0 is actually what? Constant K. And remember, in mathematics, any variable at all apart from 0 raised to the power of 0 is actually 1. So therefore, v to the power of 0 is what? 1. So we are going to have that P is now equal to what? Constant. Okay, P is now equal to K. So it means that when a polytropic index is 0, then pressure is constant. And that gives us what is called a constant pressure process. And a constant pressure process can also be called an isobaric process. Hence, when the polytropic index of expansion or compression is 0, we have what is called an isobaric process or a constant pressure process. Okay, now let's consider when n is equal to 1. If we consider when n is equal to 1, from the law, PV to the power of n is equal to constant. So if n is 1, it now implies that P v to the power of 1 is equal to what? Constant. So which simply means that PV is actually constant. Now, PV equal to constant arises from what is called Boyle's law. Recall in Boyle's law we said that the volume of a given mass of a gas is inversely proportional to what? Its pressure, provided temperature is kept constant. Okay, so that means this law or this condition is actually a constant temperature process. So when the polytropic index of expansion is equal to 1, then we have what is called a constant temperature process. Another word for constant temperature can be called an isothermal process. So when n is equal to 1, we have an isothermal process or a constant temperature process. Okay, now let's consider when n is equal to infinity. If n is infinity, then from the equation of polytropic process we have PV to the power of n is equal to constant. Now let's take the end root of both sides. Let's take the end root of both sides. We are going to have that the end root of PV to the power of n is equal to the end root of a constant K. And of course, the end root of a constant K. And of course, the end root of a constant K still remains a constant. So we have the end root of PV to the power of n is equal to K. The end root of a constant remains a constant. Now, let me just show you a little trick. Remember that if you have the square root of 4, mathematically, this is actually 4 to the power of 1 over 2 by indices. Also, let's say I have x or the square root of x squared. The square root of x squared, this is also saying x squared all to the power of 1 over 2 from indices. And of course, if you expand the bracket, we're simply going to have the x raised to the power of 2 times 1 gives us 2 all over 2. And this simply was x. Okay, so we'll have this. So that means we can as well break this equation. The end root of p to the power of n is simply pv to the power of n all to the power of 1 over n, and that's equal towards k. Alright? So, and if I expand this bracket, I'm going to have p to the power of 1 over n times v raised to n all to the power of 1 over n is equal to k. Okay, so p to the power of 1 over n will now give me v. If I also expand the bracket, I'll have n times 1. This gives me n over n equal to k. Okay, so this is actually p raised to the power of 1 over n times v, because n over n is 1, and that's equal to k. So we're simply saying that take limit, okay, as n tends to infinity, because we are considering when n is tending to infinity. So we are simply going to have p to the power of 1 all over, this becomes 1 over infinity times 3 is equal to k. But remember, in limits, 1 over infinity is simply 0. So we are simply going to have p to the power of 0, v is equal to k. And any variable to the power of 0 is always 1. So e to the power of 0 is 1. So this simply implies that we have v to be equal to what? Constant. So volume is constant. So when the polytropic index is actually infinity, then we'll have a constant volume process. And a constant volume process can also be called an isochoric process. Okay, so these are three major conditions or processes, three major conditions or values in which the polytropic index of expansion or compression are of utmost importance. First at 0, second at 1, and thirdly at infinity. So when n is equal to 0, we have a constant pressure or isobaric process. When n is equal to 1, we have a constant temperature or isothermal process. Meanwhile, when n is equal to infinity, we have a constant volume or isochoric process. Alright guys, that's it with polytropic index. In the next video, I'll talk about the work done in polytropic index. I will derive the equation for work done in polytropic index, in polytropic process. Sorry, I'll derive the equation for the work done in polytropic processes. Alright, in the meantime, do well to subscribe and of course like and share the video. Thanks and cheers.